Hi folks, this is Stan Forster, and we're going to be talking about resistors in series and in parallel. Alright, so let's go ahead and let's take a look at the parallel situation first. Let's go ahead and pull up the relevant equation. Okay, so 1 over the equivalent resistance is equal to the sum of the inverses of all the resistors, resistors 1, 2, and 3. Okay, so if we were to say, let's say, set these resistors equal to 10 ohms, so 1 over the equivalent resistance is equal to 1/10 plus 1/10 plus 1/10 or 3/10. We could, of course, just flip that fraction over, and the equivalent resistance is equal to 10 over 3 or 3.33. All right. So let's go ahead and look at an actual physical example. Okay, the three resistors in parallel, we just showed an equation that says that the resistance is going to be 1/3 of that. Okay, so whatever voltage we have here and whatever resistance we have here, okay, so we'll go take that voltage divided by the resistance. We're going to, whatever the resistance we have here and whatever voltage we have here, we can divide one by the other and we can come up with the current. Okay, so let's go ahead and let's close the switch here and let's see what current we get with just one resistor here. That's 9 amps. Now, the rule for adding resistors in parallel says that if I add both of these together in parallel, 1/10 plus 1/10 is 2/10. Flip the fraction over. We got 5. We've cut the equivalent resistance in half. We've cut the equivalent resistance in half, and the current should double. There we go. And we went from 0.9 to 1.8. So let's see if we can make a prediction if we add one more resistor in parallel. Well, we had one resistor. Let's go ahead and let's open this up here. We had one resistor. Okay, and that gave us 0.9. Okay, we'll close that again. 0.9 amps. Okay, so adding another resistor doubled that. Okay, adding a third resistor in parallel. Okay, so we went from, remember, we're adding 1/10 3 times, so 3 over 10, flip the fraction over, 10 divided by 3, 1/3. Okay, we've taken the equivalent resistance of these three circuits in parallel is 1/3 of what it is for one. Okay, we've dropped the resistance way down. Same voltage, we drop the resistance by a factor of 3, the current should jump by a factor of 3. So let's go ahead and let's put this back together. Let's close the switch, and if it was 0.9 before, it should be 3 times that, or 2.7. So let's go ahead and let's close this one here. And let's go ahead and take a look at what do we get for series resistors. Here's the rule for series resistors. I didn't even bother to throw some numbers into this one because we can add, right? So if it's 10, 3 resistors is 10, or excuse me, 1 resistor is 10 ohms. 3 of them is going to be 30, 2 of them is going to be 20, 1 of them is going to be 10. So let's come back to our construction kit here. See what we have. Okay, so we have our same voltage, 1 resistor, it's going to be 0.9. Alright, now let's go ahead and open that up. If I take 2 identical resistors, place them in series, I'm doubling the resistance. I'm adding those up. 10 plus 10 is 20. It was 10, now it's 20. So instead of 0.9 amps, it's now going to be half of that, 0.45. And so that's exactly what we see. 3 resistors in parallel, 10 plus 10 plus 10 is 30. I'm now dividing that voltage by 30 instead of by 10. Okay, it's going to be 1/3 of whatever its original value was. If it was started at 0.9 amps, we're divide that by 3, it should be 30 amps. I'm sorry, 0.3 amps. All right. Okay, I hope that cleared up the application for you a little bit and answered the question. I wasn't real clear on the question that you actually had, so I hope that helped. I'll get that posted so that you